Alright, this is the mechanics paper from 2020, Pearson Edexcel, just regular A-level maths. Let's just go straight into it. You've got an inclined plane bottom here, you draw it out. Tan alpha is 3/4. If you press tan inverse here and work out what alpha is, I think you're a pleb. What I actually think you should do is just draw the triangle. Tan is opposite over adjacent, so 3/4. 3/4 triangle, obviously, sine alpha is 3/5, cos alpha is 4/5. Good. We put all our forces into the diagram, so mg going straight down, mg cos theta going this way perpendicular to the plane, mg sine theta going down parallel to the plane. The reaction force is obviously also going to be this, mg cos alpha, and the mu, there is a frictional force coefficient mu, so the frictional force going this way is also going to be mu mg cos alpha, just mu r, mu mg cos alpha. Good, so we've got all our forces here. It's on the point of sliding down the plane, but it's in equilibrium, so this force equals this force, so we just put that down. I can also, because I worked out sine alpha is 3/5 and cos alpha is 4/5, I can just place those three with 4/5 and that one with a 3/5, and I get all of that. And now I can say, this thing equals this thing. What have I put here? Oh, part A was just tell us the normal reaction, that one there. Okay, cool. Part B is, this equals this. We can obviously cancel the 5s, cancel the mg's, and you get 3 equals 4 mu, which you divide to get 3/4 equals mu. Good. Next bit, not supposed to do any more calculations, fine. Brick B is removed and a heavier brick is placed on the table. Explain why a Q remains in place. Do you see this bit where you cancelled the M's here? That means the M's don't matter. So when you put a much heavier brick on here, it's definitely not going to matter. Brick Q is now projected with the speed down the greater, so it's projected this way with some impulse. Describe the motion of Q. Well, the forces are still going to be in equilibrium, right? Because the resistance is working as hard as it could. This gravitational force isn't changing. You've pushed it down the hill, but that pushing force is just a singular push, right? So this force is still going to balance with this one. So there's not going to be any acceleration on the object. It's still going to be in equilibrium. It's just going to move at the constant speed that it was set at after you pushed it. So it will just continue going that speed, presumably until it reaches the bottom of the hill. Good. Question number 2 then, we have acceleration this. This is a suvat question. You can just do suvat with vectors here, so we're going to use this here because you've got the acceleration, we've got the initial velocity, we've got the time, we want the final velocity, so we just plug all those things in. This just times by 2 to make 8 minus 10, and you put it together and you get your answer. Here we have something going through the origin, and then it says it goes to the point A when t is big T. The position vector of A is this. Find the value of t. So we want the vector that describes its position, and to get that we'll do r equals ut plus alpha at squared. No idea why this just becomes an r in vector world rather than the s that you usually see in suvats. But whatever. There's an r here. We plug in u, which is this again. We plug in a, which is this again. We have t as the thing that we want to solve for, so we'll just replace that with big T, I guess, which I never bothered to do, but okay. But we also know the displacement vector is this, right? This position vector is this at that time, which I should have written as big T, but I couldn't be bothered. But now we can just read across the bottom of these vectors to say minus 0.5, 4.5 equals 2t plus a half times minus 5t squared. So that's just reading along the bottom of these vectors here. And I can solve that for t, right? It ends up being this quadratic. Calculator says this, ignore this, because time can't be negative unless you have a time machine. And then we just say, okay, well, to find the value of lambda, we just read along the top row and just use the t value that we just found. And we get this. Good, and we're done. Excellent. Question number 3 then, we've got something to do with, so we've got acceleration given in terms of t. So this is a dead giveaway. This is that question they always ask about integrating and differentiating to go down the ladder of SVA, displacement to velocity to acceleration, differentiate to go downwards, integrate to go upwards. We've got the bottom of it, right? We've got the acceleration, so that's going to be, if we integrate that, we'll get the velocity. So let's integrate this thing here. And we get this. We can just integrate the two vectors separately, so this integrates to that, and then this integrates to that. We have a plus c, of course. When t is 0, so just put in t as 0 here, we get the velocity is 36i. But of course, making t 0 just makes all of this go away, which means c is just that extra thing there, and we have our velocity as this. And then find the velocity when t is 4. So we just shove in t as 4, and we'll get our velocity, and we'll have quite a lot of work there for 3 marks, I thought. Doing a whole integration, finding the constant c, and then putting something back in. Yeah, but whatever. B, find the value of t, the instant P is moving direction perpendicular to I. If it's moving perpendicular to I, now I is the horizontal vector, right? So perpendicular to that is just vertical. So we're looking for when this V is just going vertically. And for it to be just going vertically, we want the I components to be 0, right? We don't want it to be moving horizontally. So the I components have to be 0. So this and this need to be 0. Sorry, I didn't finish this off. Sorry, finished off now. Good. So that's to finish off part A. Part B, I've grouped this V, I've put this study 6 into here, because again, I want the I component to be 0, so we just put that equal to 0. This actually solves, you can use a calculator, obviously don't use T as -4 again, so T is 4.5, and that'll be my answer. And then part 2, there's a different particle here with a different equation of motions and stuff, so we can ignore everything we've just done. We are looking for the speed, which is to do with the velocity. We've got the displacement here, or the position vector thingy. So let's differentiate that to find the velocity. So we differentiate this to find the velocity. And speed is just this component squared plus this component squared, square rooted. But I can just say 5 squared equals this squared plus this squared, I think. And then obviously, I mean, this is just the 3, 4, 5 triangle in disguise, I believe. So this is equal to 4. You could also say it's equal to -4, but that gives you a negative t anyway, so it doesn't matter. And I remember when I was doing this, I thought that the first bit was a bit too much for 3 marks. This feels like too little for 6, right? I've written down 1, 2, 3, 4 things and a half things maybe, and I've got 6 marks for that apparently. So that's interesting. Question number 4 is there's only 5 questions on this paper, so we're steamrolling through it. We've got sine alpha is 4/5. Again, don't work out what alpha is. Just draw a triangle. I'll say before I begin this, I typed this entire question up using little m as my mass, just because that's what usually is the case, and then realized that they'd used big M, and I couldn't be bothered to change any of it. So I'm now officially going to set little m equal to big M, and we're just going to pretend that's fine. So sine alpha is 4/5. Again, the 3, 4, 5 triangle means cos alpha is 3/5, and tan alpha is 4/3. Good. Let's draw some forces in here. So mg, because remember little m is equal to big M here, so that's fine. I can do this. Mg cos theta going this way. We've got a reaction force off of this object here, which I'll just call R. We can split that if we want to into its horizontal and vertical components. Now just be a bit careful. Sine theta is going to be this one, because there's a few ways of thinking about this, but if this is alpha here, alternate angle says this is alpha here. You could call this 90 minus alpha, and then this one would be alpha because that's 90, and then opposite the alpha is your sine theta. So you can play that through again if you just wanted to follow the angles there, but this one is sine theta and this one is cos theta. Sorry, alpha. If I've said theta a few times, I mean alpha, of course. Just like my m's. I should also just write here alpha equals theta, and then I can get away with whatever I want, can't I? So anyway, we're making progress here. We've also got a reaction force here, which we'll just call F, I guess, because I don't want to call it R because I've called that one that already. We've also got a resistance force, frictional force here, so that's going to be mu r, or really mu f, going this way here. It's in limiting equilibrium, so the frictional force is acting as much as it possibly can, so I'm okay to write that. And now there's a few equations I can put down. Obviously I can replace all these cos alphas with these things and sine alphas and so on, so I'll replace all those to get this. And now I've got 3 equations I can write down, which is good because I've got 3 unknowns. I've got mu, r and f as my unknowns, but I can write 3 equations because I've got to balance the vertical forces, so f plus 3/5 r equals mg. I've got to balance the horizontal forces, so mu f equals 4/5 r, and I've also got to take moments. I always take moments around the base here, so taking moments here. Now how far away is this force acting perpendicular to the ladder? Well, it's a uniform rod, I think it says somewhere. I'm sure it does somewhere. Yeah, there it is. So this is going to be half the way along the rod, so that distance is 3a, so it's going to be 3a times 3/5 mg, turning this way, and then turning the other way. Now how far away is this thing here? Well, it doesn't actually say that, except it does, because if sine alpha is 4/5, then you can see my triangle here. You could just times all these sides by a to get 4a, 5a, and because that's 4a, that means this is 5a. So turning this way, we've got 5a times this force there, r. So those are our 3 equations. We've got 3 unknowns, as I said, so we should be able to solve this. The first thing it wants is what I've called r. So that's the first thing it wants. And actually, if you look at this one only contains r's anyway, so I can just do this immediately. 9 there, cancel the a's, divide by 5, and we get this. Good. So we've shown what we want to show because, of course, little m is equal to big M, so good. Hence or otherwise, find the value of mu. So okay, let's shove this r into both of these equations. So that's putting it into this one. I think from here I can solve for f, which will be useful because then I can put r and f into this one to solve for mu. So okay, multiply that out, and then this is 125 or 125 of these minus these makes this, and then put that into there and that into there, and we get this, and then we do some stuff, and we end up with this. Good, and we have mu. Excellent. Last question then. A SUVAC question. Excellent. So we've got 45 degrees here, so the horizontal component is u cos 45, vertical is u sine 45, which is u over root 2, or u root 2 over 2. It doesn't really matter how you want to write that. Okay, so that's good. We have SUVAC going up and down and SUVAC going left and right. We'll do each separately. So up and down, we have an acceleration of minus 9.8. It hasn't told me to take any other value, so I'll just use that. Acceleration left and right is 0, because there is no acceleration left and right, because there's no air resistance or anything like that, so that's good. Initial velocity up and down is u sine 45, u cos 45 going left and right. Final velocity going left and right is also u cos 45, because there's no acceleration, so it must be. We're not actually going to use that at any point, though. Now, it travels 100 meters horizontally, and it travels minus 25 meters vertically to get to here, which is kind of this first situation I want to think about, because it's the one I have most information on. T, of course, is the same for both these two things. That's the one that transfers, because the amount of time it takes to go 100 meters horizontally is the amount of time it takes to go 25 down, because it's the same system. So good, I think I can use this to solve for T. Here are all my SUVAC equations from the formula book, so I'll use this one maybe. Now, if you use these over here, you can actually put them into any of these. You get exactly the same sentence, which is this. All right, so I think I probably, you can test it yourself, but you just get this expression over and over again. So that's good. It's got u and t in it. There should really be a bracket here, really, because this isn't cos of 45t. It's cos 45 times t. So there should be really a bracket there, but whatever. I'll accept it. Or just put the t here. Whatever. So I can also make an expression using this one. Just take the equation that doesn't use v, which is this one here. So we'll put that into there, and we'll get this, I believe. By the way, these are of course negatives because they're going downwards. I didn't mention that. I'm taking upwards to be positive, and I was taking to the right to be positive as well. So okay, we get this. I think I'm looking for u, so I may as well get rid of t here by rearranging that. Cos 45, as I said, is 1 over root 2, so times by root 2 to get it over here, then divide by u, and then take this and shove it into here. The u's cancel. This is 1 over root 2, which will cancel with that. So this ends up just being 100, all of this. You've got a calculator, so you don't actually need to know the exact value of this, but it's fun to know. And yeah, we square this out. 100 squared times 2, roots 2 squared is 2, and then we get this. And then we can, of course, just rearrange this, which looks like this. We can divide by that. We can flip this over. We can square root. Eventually, you'll get to this. I'm sure you can follow that yourself, and we get to this, which is our answer. Excellent. So we have the thing. Find the greatest height of the ball above the horizontal ground NA. This is actually the one question I lost a mark on, which was disappointing. I'll explain why I did in a second. Firstly, I'm just going to shove in u is 28 and cos 45 is 1 over root 2 and so on to get these results here. And now I've got rid of the displacements because I'm actually thinking about a different situation now. I'm thinking about the situation about it getting to the top of its journey. Now, when it's at the top of its journey, its vertical velocity is 0 momentarily. Right when it's at the top of its arc here, it's not going up or down with any speed here. So this is going to be 0, and I want to find out this distance that it's traveled upwards to get there. So okay, I think I've got enough information. Just don't use the equation that uses t. So I'll be using this equation here to find my s, and that's this. U is 0. V is 0. U is this. And then 2as. Solve that for s, it ends up being very straightforward. S is 20, so it goes 20 meters up. I therefore finished that and said the answer was 20. The answer is not 20 because it says the greatest height above horizontal ground NA, so you have to add that 20 meters it's gone upwards to the 25 to get the answer of 45. And the last 2 marks in the paper are just for saying some words. If you include air resistance, how would the value of u compare to what it did before? Well, if it still has to go 100 meters across and there's air resistance, you're going to have to fire it faster, right? Because there's air resistance, frictionally bringing it back, sort of. So you just have to make U bigger. Otherwise, it's not going to go as far, obviously. State one further refinement to the model. Good old particle thing. Just don't model it as a particle, and you get the mark there. Excellent. I think that's the whole paper. Thank you for watching, and I'll see you next time. Which I always say. Why do I always say that? It's such a dumb thing to say. I won't see you. I never see any of you, and you never see me. You just hear my voice.